All right, so we continue with our coverage, and today is probably one of the most important lectures, I think, of the whole course, where we finally converge to the situation where we can solve indeterminate structures. We are going to be now putting together the expertise that hopefully you've developed in the last few weeks on how to be able to compute deformations for arbitrary structures. With regards to the exam, by the way, we haven't had time to look at it yet. We'll try to get to that in the next few days. Today is Wednesday, so hopefully by next class, next Monday, it would all be done. Okay, so let's see. Last time we talked about, or I talked about the fact that statics is always valid, right? I mean, structures have to be in static equilibrium, but statics does not suffice to solve a significant number of structures, right? And when statics is not sufficient, we then refer to these structures as statically indeterminate. I already presented a discussion indicating that even if a structure is statically indeterminate, it doesn't really mean that there isn't a number of quantities in the structure which can be calculated only from statics, and I showed you the example. But the conventional use of the language, of the term, in civil engineering, in structural analysis, is that if there are some stress resultants, moments, shears, and so on, that cannot be computed exclusively from statics, then we refer to the structure as statically indeterminate. The method that we're going to be developing today comes under different names, but classically is known as the force method of analysis. Okay? It's the force method of analysis to distinguish it from the displacement method. The displacement method is not covered in this class, but what it is important to note is that the force method of analysis is fundamental. Mainly it stands on its own. The displacement method is not as fundamental as the force method in the sense that, well, it depends what level of sophistication one carries the discussion, but let's say in the normal standard sense, this is uses results derived from the force method, right? So in that sense, the displacement method is less fundamental than the force method, right? Now, this is also usually referred to as matrix methods of structural analysis and so on. The force method then, which is the one that we were going to be developing today, is often referred to also, and we will use that terminology, as the flexibility method. Okay? The force method or the flexibility method are the same thing. The name force method comes from the fact that the unknowns, traditionally of course, are usually forces. Forces meaning in the general sense, forces, moments, and so on, right? And the term flexibility method comes from the fact that when you formulate the method, you end up having a mathematical structure in which one matrix that is involved is the flexibility matrix, which will become apparent as we go. Now, let's see. The force method or the flexibility method builds on the idea of linearity, that is, the structure is supposed to behave linearly, uses superposition, and that's why That's why we need linearity, because we're going to be using superposition. That is, we're going to assume that if we have something that produces an effect A and something else that produces an effect B, that the action of the two things together produces A plus B. Now that does not happen if the system is nonlinear, right? But we are assuming linearity and superposition. So that we can use superposition, and we will then exploit constraints. That is, constraints meaning we will exploit the fact that we can say this point has no deformation, or we know the deformation, or this point has no slope, or we know the slope, and things like that. Now, let me begin the discussion by presenting things without numbers. We could, of course, jump right away to step one, step two kind of thing, but hopefully taking a time to try to build the fundamental understanding of what we're talking about is worthwhile. So let's begin just by calling on intuition and seeing what we're talking about. So let's consider this beam to start with. So this is a simple beam with some load. I mean, not a simple beam, a beam under 3 supports, and it's got some arbitrary loading. So the first thing that we ask ourselves is this structure that we can solve using statics? And we conclude that now we really cannot solve it completely. When I mean solve it, let's, for example, draw the shear and moment diagrams. We cannot do that from statics only because, of course, here the horizontal reactions are 0 when I'm talking about beams, so I don't count the horizontal. I would say there's 1, 2, and 3 reactions, and we only have 2 equations of statics, right? Or you could say there's 1, 2, 3, and 4, and we have 3 equations of statics. So we have too many reactions, we can't solve for them, right? There are no internal hinges, there's nothing else to take advantage of. So we normally would say, that, well, not normally, we would then say this structure is indeterminate, and the degree of indeterminacy, as we discussed in the last class, is 1. Now, once we decide, or we not decide, once we identify that the degree of indeterminacy is 1, that means that there is one thing that we could remove from this structure, one stress resultant or one reaction, and the structure then would be statically determinate. So, for example, we could take this reaction as being the extra quantity, right? And our extra quantities would be called X. So let me put it this way first in this discussion. Forget about procedure. You agree that this sketch A and this sketch B are equal to each other for the correct value of x1, right? If x1 has the value of that reaction, then these two sketches are identically the same, right? Of course, we don't know x1, but I'll repeat myself at the risk of being redundant here. This is the real situation. This is just a sketch of the same thing in which I've given that reaction the name x1. I don't know what it is, but instead of treating it as a reaction, I think of it as being a load that has a name x1. Now, if we then say that situation, which is the same as the original one, can be broken into 2 parts because this problem is linear, and therefore we can separate it into pieces. So in my first examination, I take the case where x1 is equal to 0. And so I have a structure like that. That structure is statically determinate, right? 2 reactions with an overhanging part, no problem. So we can say that that structure will have some sort of a deformation, and it doesn't really matter whether this sketch is correct exactly or not, but let's say it deforms like the dotted line, right? And we could give a name to this deformation here, and we just call it A for now. So the tip of this structure here move down by A. So this is equal to this plus, right? In this part we had no x1. Therefore, we must add the effect of x1, right? Now, we don't know the value of x1, and notice, by the way, that the load, this is the real thing, right? Let's start again. This is the real thing. I just identified that it was indeterminate to the first. This is the same thing, except that this reaction has been called x1. And this is the same as this one, not this one, but these last two sketches, in other words, A, B, C, and D. So C plus D are equal to the sketch B, right? C plus D are equal to the sketch B, which is the original one. Now, in this particular instance, this structure will deform due to some value of x1, let's say like this, right? And this deformation here would be something, right? Now, it's clear that, well, let's see, how would it be easier to say this? I guess I'm trying to decide whether to get mathematical or not. There is a value of x1 for which this is A, right? And that value is going to cancel that A, so this plus this is the real thing. Correct? Now, this displacement here could be, let me call it n, right? So if I call that displacement n, then I can write here in words, it is clear that nx1 must be selected such that n is equal to A, right? So if I choose the value of x1 so that this moves up A, then I can say that is the reaction here, because this sketch C plus sketch D will then not only be equal to this thing, but satisfy the constraint that the movement at the location of x1 is actually 0. Okay? So that's one first look at it. Let's take a look at another one and sort of press the point. Let's say that we consider now a beam that is fixed on this side and has a roller on the end. And again, it has some loads. Once again, we look at it and we say, okay, if we didn't have this reaction, that would just be a cantilever. I really don't need that reaction there to have static equilibrium. So this structure is really indeterminate because it's got this one thing, right? Or if you want to count 3 reactions plus 1 is 4, my free body diagram only has 3 equations. So this is again indeterminate to the first, right? Now, the question is, what kind of extras can I select? Well, this is equal to this, right? And this is the redundant. The x's are called redundants, right? So I could say that it's equal to that. But I can also say, why use that one? I could use this one. I could just turn this fixed end into a pin and call this the redundant. In other words, the moment that is there in reality, I'm going to call it the unknown. So, oops, sorry, I have to put the load here, right? So that is the same as this, and so is this for the correct value of x1. What is the correct value of x1 here? The value for which this situation has no deformation at point B, right? The value of x1 here is the value for which this sketch sketch A, sketch B, sketch C. So sketch B needs a value of x1 so that the deformation at point B is 0. Sketch C needs a moment x1 at A so that the rotation at A is 0, right? Can I use another one? Yes, I can, right? I could do this too. I don't want to use the moment. I don't want to use the reaction. And I'm going to do this, which is less evident, let's say, but I'm going to put a hinge here. If I put a hinge at that point, this structure is statically determinate, right? Because there are 3 reactions here, one here, which is 4, but there is one point where I know where the moment is 0. Or, if you want to see it from the point of view of free body diagrams, you are able to take a free body diagram of this loop, of this bubble, and another free body diagram of this bubble, and take advantage of the fact that both of those free body diagrams do not have a moment at the location of the hinge. So if you are looking at bubble number 1, then bubble number 1 would have 1, 2, and 3 unknowns, 4 and 5, right? So 1, 2, 3, 4, and 5, there is no moment here. If we now take a look at bubble number 2, over here, we'd have the same 4 and 5, right? In opposite directions. And on this case, we would have 1 new and 6. So there are 6 total unknowns and we have 6 equations. And so we obviously can solve for everything because there's equal number of equations and unknowns. So I'll erase here. Erase this thing and draw it again to make the point that there are instances where it's a choice and there are instances where it's not a choice. In this case I put here a hinge, and so I can say that this is also equal, and now my unknown x1 is the moment that exists at that hinge, at the location where that hinge is on the real thing, and that I have to replace by x1. Excuse me, there's a call here, let me cancel it. Hello. Excuse me, wait, let me stop here. That was